Thank you all for coming. I hope you're in the right place. If you're expecting me to be more Australian and be Christopher DeBella, sorry to disappoint you. So my name is Tristan. Chris, unfortunately, is not well, so the second half of his talk is being moved to tomorrow. This is a last-minute substitution. I'm also doing a talk tomorrow, a different talk, a new talk, but as a sort of last-minute substitute, rather than having an empty room, I'm going to be doing or redoing a talk I gave last year. You can see there's an off by one error in the corner there. So there's like a maxim in show business that you should never tell the audience how unprepared and unrehearsed you are. So I won't do that. But please bear in mind, this is a talk I gave last year that I haven't really looked at for quite some time. So if I stutter, if it's not as good and flowing as you might like it to be, then please bear with me. The original talk was 75 minutes. We've got a 90-minute session. Theoretically, we might be finishing early. You might get a nice early lunch. Who knows? So, by the way, if anybody is in the wrong talk and wants to go somewhere else, I completely understand. Don't just please do get up and leave. If you get up and leave halfway through, I might get a bit offended. But anyway, all right. Iteration revisited. So, what is this talk about? This talk is essentially about a library that I've been working on for actually coming on for 2 years now, that aims to be a sort of safer, better performing, better, I guess, generally version of ranges and iterators and things like that. And the talk really is in two parts. So the first half of the talk is kind of the motivation for this, why I started working on it, why I think the iterators that we have in particular are, are less than perfect. And then the second half of the talk is more about the actual library itself that I've been working on. Because this is because it's a year-old presentation, there might be some things in the library that have changed. If I come across them, and if I remember, I'll try and point those out as well. All right. Is the clicker going to work? Yes, all right. So, Iteration Revisited is the title of the talk. Subtitle, which wasn't on there, was a safer iteration model for C++. So we'll start off by revisiting probably the first bit of iteration, the first loop that most of us ever wrote in C++ or in C or many other languages that have a similar syntax. So here we've got an integer array, 1, 2, 3, 4, 5. We've got this size variable telling us that the size of the array is 5. And then we've got ye olde for loop. So we're just iterating from index 0. We're continuing while I is less than the size. We're incrementing the index at each step. And then within the body of the loop, we're accessing the ith element of the array, and we're calling this do something function. Okay, so hopefully this is pretty familiar. I don't know if you're anything like me, you've probably written this like 5,000 times. But this is not the only way in which we could write an iteration loop. And perhaps if you come from a C background, you might choose to write it something like this. So here we're taking a pointer to the first element, using this array decay, taking a pointer to the first element, the address of the first element. We're continuing while p is not equal to the address of the first element offset by size places. We're bumping the pointer at each iteration. And then within the body of the loop, we're dereferencing that pointer. We're accessing the element at that address, and we're passing that to the do something function, whatever that does. So this is how you might write it in C. In C++, we've got these fancy standard begin and standard end functions. These are pretty nice because for an array of known bounds, standard end means we don't need to keep this size variable around, so that's quite nice. But actually, you probably wouldn't write this in C++ either. You'd probably write something a bit more like this. So we'd name our variable iter instead, and this now begins to look like something that's much more kind of C++-y, right? And in fact, we could go one step further and use a range for loop, but a range for loop kind of desugars to something that looks very similar to this. It's not precisely this, but it's pretty close. So actually, this transition from here using int star to here using auto iter actually tells us something really interesting about iterators, about STL iterators. And that is that STL iterators are a generalization of array pointers. Okay? STL iterators have pointer semantics. They are a generalization of this notion of iterating over an array by taking a pointer to each element. And in fact, pointers into contiguous sequences, like we just saw, they're in fact the most general, they're the most powerful kind of iterators. They're contiguous iterators. So this is the model that we've had in C++ since 1998. In fact, the library, the STL, is a little bit older than that. It's like 30 years old now. It's been around a very long time. It's been used in, I don't know, millions of code bases, probably thousands anyway. It's got a lot of things going for it. In particular, it's a really powerful abstraction. So we start off with contiguous, random access iterators, but we can have bidirectional, we can have forward iterators, we can have input iterators, right? We can write all sorts of algorithms, pretty much any kind of algorithm you can think of. We can go from, a simple, like, I don't know, for each loop, right up to doing standard sort. It's a low overhead abstraction, right? This was particularly important back when compiler optimizers were nowhere near as good as they are now, because as we just saw, you can literally use a pointer as an iterator if you want to. This one's maybe a little more arguable, but iterators have a sort of natural syntax in the sense that they use the same syntax as built-in pointers do. Right, we use operator star to dereference, we use operator plus plus to increment. But there's a pretty big downside to STL iterators as well. And that is that they are just as dangerous as raw pointers, right? Because iterators have pointer semantics, iterators are just as dangerous as raw pointers. They lack safety in exactly the same way that pointers do. So I've said the word safety, and this means that I have to take a very brief aside to answer the question, what do I mean by safety? There are lots of people doing lots of talks about safety in C++ at the moment. I'm going to be doing another one tomorrow that hopefully maybe be a bit more prepared for, we'll see. What do I mean by safety? So for the purposes of this talk, and the talk tomorrow, if you come to that, please do. For the purposes of these two talks, I'm going to use a definition of safety that comes from a talk from Dave Abrahams that he gave at cppcon a couple of years ago. So Dave Abrahams, our keynote speaker on Wednesday, gave a talk that was also about the val language, actually, or val as it was called at the time. And in this talk, it's a really great talk. You should watch it if you haven't already. In this talk, Dave gives this definition of safety. Okay, he says, a safe operation cannot cause undefined behavior. And that might be a little bit small for you to read on the screen, so let's blow that up a little bit. A safe operation cannot cause undefined behavior. And I really like this definition of safety because there are all sorts of kinds of safety that people talk about. But really, at the root of everything is undefined behavior. Because if we have undefined behavior in our program, we cannot, well, I guess it's arguable we don't even have a C++ program at all. We cannot reason about the state of our program in the presence of undefined behavior. And it's kind of worse than that because compiler optimizers take advantage of the fact that undefined behavior can never happen. And so you can actually get really crazy, unexpected things happening even before your program control would reach the point where undefined behavior would happen. You can people say that undefined behavior travels back in time, right? So we cannot have any kind of safety in our programs in the presence of undefined behavior, right? Undefined behavior is, or the absence of undefined behavior is a prerequisite for any discussion about safety, is what the point Dave was making in his talk, and that's why I really like this definition. So this is the definition of safety that we're going to use for this talk. So armed with our definition of safety, let's take a look at a couple of, well, literally 2-line examples or short examples of code using iterators and try and decide whether those are safe operations or not. Okay. I suspect 1 or 2 of you might know where this is going, but we're going to look at the examples, okay? So first thing we do is we're going to initialize an iterator that points to the end of the array, one past the last element of some range. Okay, so the first line here, this is perfectly fine. We're allowed to form an iterator that's one past the end of a range. In fact, the C++ standard, the C standard before it, gives you special permission to form a pointer that's one off the end of an array, pretty much specifically so that you can do this. So the first line is perfectly fine. Unfortunately, the second line is problematic, right? We're dereferencing a past the end iterator, and this is undefined behavior. And again, if you think about this in terms of array pointers, well, there is no object. It's one past the end of the array, so how can we possibly try to access that object via that address? Okay, so we're not off to a great start, but maybe things get better. What happens if we have our past the end iterator and we try to increment that iterator? Well, the standard tells us that incrementing a past the end iterator is undefined behavior. So if you have a bidirectional range, decrementing a begin iterator is undefined behavior. And if you have a random access range, doing an out of bounds jump, forming an iterator that is outside of the range is undefined behavior. So operator star, no. Operator plus plus, no. Not great so far. Let's carry on. Okay, slightly more complicated this time. So here I've got a function called min_iter. It takes a const reference to a vector, and then it calls standard min element with vec.begin, vec.end, and this is going to return us an iterator into the vector that we were passed in. And this min_iter function kind of looks fine, right? Like, we've got the vector, we're going to return an iterator into that vector, we're taking the vector by const reference. Surely this is all right. But what happens if I have a function like getVector here that we imagine returns a vector by value? Well, what's going to happen in that case is that we're going to pass the return value of getVector, this PR value. It's going to bind to the reference. We get lifetime extension. This is how const references work. And then that vector is alive for the duration of the call. So min element is going to find an iterator into that vector. It's going to return the iterator. And then we get to this, the end of the full expression is the technical term. We get to this closing semicolon. And all of a sudden, our temporary vector that was returned from getVector gets destroyed. And now iter is a dangling iterator. And on the last line, when we try to dereference this dangling iterator, we get undefined behavior. So dangling iterators can occur very easily. You can have, I mean, I think this code looks pretty innocuous. To me, this, you see things like this all the time. Dangling iterators can occur really easily, and pretty much any operation on a dangling iterator is going to wind up being undefined behavior. You're allowed to destroy it, you're allowed to assign to it to reinitialize it, but pretty much any trying to use it as an iterator is going to be UB. One final example, and this one really upsets me. Right? I find this one. This is just really bad. So I wonder, can anybody tell me what's the problem here? Shout out. I'm sorry? Location of data. The location of the data might change, yeah, absolutely. So the term is iterator invalidation, right? So what's going on here? Well, we're initializing this variable iter with the start of the vector. And what happens behind the scenes is that iter is effectively holding a pointer to the start of the vector's internal data, the vector's internal allocated array. And then we have this call vec.pushback. And now what's going to happen is if the vector happened to be at capacity, at the point at which we call pushback, then the vector is going to allocate a new array, generally about twice the size. It's going to move all of the elements from the old array into the new array, and it's going to delete the old array. Right? This is just how vectors do automatic growing. And so now our iter variable is dangling, right? It's pointing to some deleted memory. And so in the while condition there, we're comparing iter to vec.end. This is comparing some dangling pointer to now vec.end is going to give us the address of the end of some completely different array that might be somewhere completely different in memory. And we're comparing two pointers that we're not allowed to compare by the standard. So this is going to be undefined behavior. And what makes this particularly upsetting to me is that this is probably going to work okay most of the time, right? Because if there is spare capacity in the vector, then pushback's not going to cause a reallocation, and you're going to get away with it, right? Iter is not going to end up being invalidated, and so this code's going to work all right. So this code can be sitting in your code base for like 20 years, and then all of a sudden, maybe you update your standard library and the growth properties of the vector have changed. Or maybe someone adds a bit of code miles away, meaning the vector's a slightly different size at the start of the function. So now you get reallocation when you never did before, and now we're seeing undefined behavior where previously we got away with it. And it's kind of worse than that, because not only do you get away with it, but if you're, unless you're someone who knows C++ pretty well, there is nothing like obviously wrong with this code, right? If you're somebody who maybe uses C++ occasionally, maybe your main language, you use another language most of the time, but you dabble in C++, unless you kind of know about the fact that pushback can invalidate iterators, there's nothing that's visual in this code that says, hang on, there is something dangerous going on here. So this example really upsets me. So iterators can become dangling in ways that I think are highly non-obvious, if that's a sentence. And really, it's just all part of the C++ experience, right? There is no way of knowing in advance that this is going to be problematic. It's just, you just have to know, right? Either you read the documentation, or more likely, you've been bitten by this at some point in the past. So our statement was a safe operation cannot cause undefined behavior. And yet, as we've seen, most iterator operations can cause UB. And so this is kind of harsh, but really we put these two things together, and the only conclusion that we can really draw is that STL iterators are a fundamentally unsafe abstraction. People agree? Have I managed to convince you? Okay. So let's take a step back for a minute. Let's go back to this loop I wrote here and actually think about what's going on. Because it turns out that, and this has been well known for like, I don't know, since the 60s, maybe before that, I don't know. In computer science, this is really well known, that in order to perform any sort of external iteration, we need 4 operations. And in fact, these 4 operations are all on the screen right now. So what are these 4 operations that we need? Well, the first thing we need to do is we need to initialize some sort of iteration state. Right? We need some object, some way of storing, holding where we are in a sequence. We need to be able to check whether iteration is complete. So the initialization we do with a begin for iterators. The end check for iterators we do by comparing to this sentinel. A third operation is we need to be able to read the element corresponding to our stored state. So again, with iterators, we do this by dereferencing. And finally, we need to be able to advance our iteration state so that we're now pointing to the next element. So these four operations, again, the theory of this has been known for a long time. In fact, if you think about just the very syntax of a for loop in C, right, it encompasses these four operations. Right, we've got the three parts in the for header, and then in the body we do the access, the read operation. So our four operations: initialize, check, read, advance. Now, what's quite interesting is, although these operations are fundamental, we don't actually have to implement them as four separate functions. Sorry, go back one. It's fine. Initialize, check, read, advance. So we initialize some state, and then we do check, read, advance in a loop, right, until our check tells us that we're finished. But we don't actually need to implement these as four separate operations. In fact, we can fuse together, particularly the check, read, advance operations in various ways. And some people might be familiar with Rust iterators, for example. So Rust iterators fuse together the check, read, advance operations into a single function called next that returns you an optional. So you call next, it gives you the first element. You call next again, it gives you the second element, and so on, until eventually it returns you an empty optional, which signals that iteration is complete. So it fuses together these operations. And there are some advantages to fusing these things together. In particular, it's quite a lot simpler. It's a much simpler iteration scheme. So there's only really one function that you need to worry about, whether you're a producer, whether you're writing an iterator, or whether you're consuming an iterator. You know, you just call next, and it's pretty easy. So it's simple, but with this fusion, there are downsides as well, in that we lose some expressive power, because in particular we can't do a separate read and advance. It means that we have to call read for every element. We can't just skip elements without reading them, right? So there are algorithms that you can't write quite as efficiently with the Rust or with a fused iterator scheme. And this also makes it quite difficult to do in-place operations, right? Because you can't repeatedly read an element at a certain position. You can only advance in order to get the next element. So if you're interested in learning more about how different languages, different libraries implement their built-in iteration models, if you like, Barry Revsin has this fantastic talk. It's honestly one of my favorite talks on this subject, like ever. So he gave this at CPP Paris as a keynote in, what was that, 2021, so a couple of years ago now. It's really, really fascinating talk. So he compares C++ iterator ranges to D ranges, to Rust iterators, he talks about Java, he talks about C#, talks about Python. He looks at how all of these different languages do their iteration, and sort of the pros and cons of the various models. So really fantastic talk. If you're interested in this stuff, like I can't recommend this highly enough. So, okay, now we know what an iteration scheme has to do. Can we think of some iteration scheme that we might want to use? Maybe one that we're already familiar with, that has, or rather doesn't have the UB problems that we've seen with iterators. Well, there's one that I'm pretty sure you're all familiar with, and I'm pretty sure you're familiar with it because I happened to sneak it on as the very first slide of this talk. And that's, well, this wasn't precisely the slide, but this was close enough, right? And that's iteration using indices. So what happens if we iterate using indices instead? So here's the loop we're interested in. Well, we've still got our four operations, right? We're initializing some iteration state. In this case, it's the integer I, the size t variable I, tells us where we are. We've got an end check. We're checking whether I is less than size. And now we do something interesting. We define our read operation to be vec.at, right? So we have a bounds checked read operation. And then finally, we advance our iteration state by just bumping the size t. So what happens if we take our iterator code that we had before, but we use these new definitions of these iteration operations? Okay? We're going to take these substituted operations, and we're going to substitute those into the code examples we saw before, right? So here's the first example. Previously, we were initializing an iterator to the end of the array, and then we were performing our read operation on that past the end iterator. Well, the equivalent is a past the end index, right? We set our index equal to the size of the vector, the end of the vector. And then we perform our read operation. But we defined our read operation to be vec.at. So what happens in this case? Well, in this particular case, we're going to get an exception thrown. Now, maybe you don't like exceptions. The point is not about exceptions. The point is that this is well defined for any index we want to pass to at. We know what's going to happen. There is no undefined behavior, right? The compiler can't perform all the crazy optimizations around UB, right? This is well defined. And okay, if we don't like throwing an exception, maybe we could define a safe read operation that terminates our program instead, or however else you might want to do it. The point is, no undefined behavior. What about our second example? So we're taking our past the end index previously, as we did on the last slide, and now we're incrementing that index. So this was undefined behavior when we tried it with iterators, but this time our index is just a size t. And operator ++ is well defined for all values of size t. If you somehow, and I don't think you can do it, but even if you somehow got a vector that was of size t max, operator ++ is still well defined, right? It just wraps around. Again, no undefined behavior. This is a safe operation. And yes, this assumes we're using unsigned indices or that we have checked operations on signed indices. As it happens, Flux that I'm going to talk about, we have like this whole suite of check numeric functions. So this is going to be safe. Third example. So previously I had this min element function that took the vector. Now I've changed it so that it's a min index function. Now I've omitted the body of the function because it's not particularly interesting. It's only a few lines, but it's not really relevant. The point is, this is going to return you an index to the minimum element of the vector. So now let's look what happens if we pass an R-value vector into this function. Well, once again, it's going to bind to the const reference. We're going to iterate through it. We're going to find the minimum element. We're going to return an index to the minimum element. The end of the full expression, the temporary vector gets destroyed. And then what? Well, then we're left holding a size t. And that's it, right? Because the vector has been destroyed, and because our read operation required the vector to be around in order to even attempt to read from it, dangling indices are safe by design. We're just holding on to a size t, right? There's nothing dangerous about that. We can't even try to do an out of bounds read because we can't perform a read at all because we no longer have the vector to try and read from. Okay, this is the last example. This is the one that I really, really hated. This is the one that upset me. So previously we were initializing iter with vec.begin. Now we're initializing index to the start of the vector, so index 0. Then we're performing a pushback. And then we got the while condition, and this is fine, right? This is going to work. This is not going to be a problem because the pushback hasn't invalidated the index. The index is still valid, and the while condition is not going to be UB. We're happy. Everything is good. Everything is fine. Now, this doesn't mean that you can't have index invalidation. So if we had a vector of size 1000 and we're holding index number 900 and then we resize the vector so it's now size 10, our index is out of range. But the next time we try and read, it's going to be bounds checked. So we're going to get well-defined behavior. And comparison against the size is also well-defined. Right? Index invalidation problems are no longer undefined behavior. They occur in far fewer situations, and even where they do occur, they can be caught by the bounds check and the next attempted read. So I hope you agree with me that index-based iteration with a bounds checks read operation dramatically reduces the potential for undefined behavior compared to iteration using indices. Using iterators. Is that reasonable? Yeah. But of course, it's still just as powerful because we can do random access into a vector using, or into any random access array type using indices, right? We do this all the time. You can access anywhere in a vector in constant time. It's still just as powerful. We can write a sort algorithm if we want to that uses indexing. It's just as powerful as using iterators. So here's the big idea. What if, instead of doing what the STL does, which is to start with the idea of iteration by pointer and generalizing backwards from there to weaker iteration categories, what if we started with the idea of index-based iteration and worked backwards from there instead? What if somebody did that? Wouldn't that be nice? Wouldn't that be nice if somebody had written a library based around these ideas? Well, fortunately, somebody has done just that. So this library is called Flux. The URL is on the screen there. And as I say, it's a C++20 library exploring these ideas. Excuse me. So what are the aims of Flux? What do I want to achieve with this? Well, first of all, what we've been talking about so far, much improved safety by default compared to using STL iterators. Hopefully, improved ease of use, fewer gotchas, surprises. People have used ranges. There are a few things in there that you kind of raise an eyebrow to the first time you come across them. Hopefully, Flux has a bit less of that. Flux aims to have equal or better runtime performance than C++20 ranges. So if you can afford to use ranges in your code, you can afford to use Flux. So I'm going to talk about performance towards the end. And finally, compatibility as far as is possible with existing STL code. And I'm going to talk about that too. Okay, so we've seen what our fundamental iterator operations are. So let's look at how we spell these things in Flux, right? So function Flux first returns you an object called a cursor, which is an abstraction of a sequence position, right? This is a generalization of an index. So it so happens that for contiguous sequences, this is literally just an integer index, but it doesn't have to be. Cursors in general can be any type that makes sense to represent a position in a particular sequence, right? And we have a function called isLast. Pass it the sequence, and you pass it the cursor, it returns you a bool to tell you whether iteration is complete or not. We have a function readAt. So you pass it the sequence, you pass it the cursor, and it returns you the element at that cursor position. And finally, we have this operation increment, that takes the cursor by reference and it increments the cursor in place. So these are the fundamental operations in Flux. This is how we write them. And what you'll notice, well, two things really. The first is that the isLast, readAt, and inc operations, they all take the sequence as their first argument. And what this means is that it's very, if we have a situation where we're holding onto a cursor, but the sequence itself has died, we no longer have the sequence available, then we can't actually call any of the iteration functions, right? So this thing I was saying about how we sort of dangling iterators, dangling, what did I say, indices are not problematic by design, that applies to Flux cursors as well. The second thing is that in Flux, we require all of these operations to be safe. That is, to not cause undefined behavior, no matter what kind of cursor we give or what sequence, or as far as possible, what sequence we use, right? And this is important because like safe operations compose in the sense that if our basis operations are safe, then the things we build on top of those basis operations are going to be safe as well, in general. So Flux is a C++20 library. It makes pretty heavy use of C++20 concepts. And a type which provides these four operations, we say it models the sequence concept. So I couldn't reuse the term range because that would be really confusing. So in Flux, I call it a sequence. Now, the term sequence is also overloaded, but you've got to call it something. So in Flux, this is a sequence. And as with the STL, we assume that sequences are single pass by default. Right, so once we have iterated past some element, we can never go back to it. So this is the same as input ranges in C++. Of course, we also have multi-pass sequences. And multi-pass sequences are those which allow simultaneous iteration by multiple independent cursors. So these are the equivalent of forward ranges in the STL. So what it means is that we can write more sophisticated algorithms. We can save a particular cursor position. We can have a second cursor. Maybe the second cursor goes off and iterates up over there. But then we can call read again on our saved cursor position, and that's just going to work fine. That's what we mean by multi-pass. We can have n cursors all iterating independently, and that all works. So that's what multi-pass means. That's the difference between forward ranges and input ranges in the STL. That's the difference between multi-pass and single-pass sequences in Flux. So the multi-pass, amongst other things, the multi-pass sequence concept requires that the cursor type is what we call a regular type. That is, it's default constructible, it's copyable, it's equality comparable. So what this means is we can copy a cursor to save a particular position in the sequence, and we can compare two cursors to say, do you represent the same position? Right? This is quite important for building up algorithms. So for multipass sequences, cursors are required to be regular types, and conversely, if your cursor type is regular, then we assume the sequence is multipass. Because it turns out that just semantically, cursors for single pass sequences kind of should be move only. Because we can't save a cursor position, we don't want to be able to copy a cursor for a single pass sequence, right? So there is an opt-out, like a sequence can say, hey, I know my cursor's regular, but I am actually only single pass. It turns out that although I put this in, none of the built-in sequence types in Flux actually make use of this opt-out, because in Flux, the built-in sequence types, they all only have move-only cursor types for if they're single pass. So we can go further, we can have bidirectional sequences. So these are multi-pass sequences that additionally allow us to decrement cursors, right? So these have an extra function, the counterpart to inc is decrement, and this, again, takes the cursor by reference and decrements it in place. So these are like bidirectional ranges. We have random access sequences that provide some additional operations again. So first of all, they have an overload of inc that takes a signed offset. And what these do is they, as you might imagine, they move the cursor in constant time to the new position. Again, they take the cursor by reference. Random access sequences have a distance operation. So given two cursor positions, we can say, like, how many elements are there between these two positions, right? Or another way of thinking about it is how many times would I have to, what offset would I have to give to inc in order to get from to to. Random access sequences also require that their cursors are totally ordered. That is, that we can take two cursors and we can say, is this position earlier or later in the sequence than this position? Okay, so these are, not coincidentally, pretty much the same requirements, like differently stated, as there are for random access ranges. And finally, we have contiguous sequences, which like contiguous ranges, they're random access, they're backed by an in-memory array. It means we can, in some circumstances, do low-level operations like memcopy when we know we've got trivial types and things like that. Oh, so you do a talk after a year and you forget what slides are coming next. There are a couple of other concepts that are kind of less important, but just include them for completeness. The first is bounded sequences. So the way we check for the end of iteration in Flux is using a function called isLast, right? So we don't actually require the sequence to be able to form an end cursor in constant time. So this is kind of the equivalent of sentinels in C++20, if people are familiar with that. However, a lot of sequences can provide you with a pass the end iterator in constant time, and when they can, this can be pretty handy for implementing certain algorithms. So this is the equivalent of a common range. People are familiar with C++20 ranges. So these sequences, we call them bounded sequences, and they provide an extra function called flux last. This gives us a pass the end cursor that we can iterate up to. We have sized sequences. These are ones that know their size ahead of time, can tell us their size in constant time. Again, the equivalent of sized ranges. And they provide a size operation. And finally, there's something that's going away, so don't worry about it. But we have infinite sequences, currently have infinite sequences, but they're going to be going away. So they were sequences that statically guaranteed that they never terminated. Turns out this is less useful than it might appear and also problematic in some circumstances. So don't worry about that. So again, if you're familiar with C++20 ranges, you can see that there's a really, really direct correlation between the Flux sequence concepts and the range concepts, and even a direct, pretty much one-to-one mapping between the Flux operations, these four things I talked about, and the iterator operations, operator plus plus, operator star, etc. And this is not by accident, right? This is because I want to make something that is reasonably familiar to C++ programmers, but also because it allows pretty much almost mechanical translation from algorithms that use iterators to algorithms using the Flux primitives instead. Right? It is really, really easy, or okay, I think it's easy, to take an algorithm written using iterators and convert it to use these safer Flux primitives instead. And so Flux has a whole bunch of algorithms included in it. So this is a little bit dated now, as you can see, because this is when I gave the talk last year. But it has a whole bunch of named algorithms. They are the equivalent of a lot of the STL algorithms. So there are like, what is it, like 105, 110 algorithms in the STL. We don't have quite that many in Flux yet. We have a number of important ones. So these just come with a library, and they do the equivalent of what the STL algorithms do. They take a range, or take a sequence, I should say, and either modify that sequence in place, or they perform some calculation, give you some results, like the STL algorithms that we all know and love. But we can go further, because C++20 brings in the ability to write lazy pipelines, right? Views, people call them, right? So you can take your vector and then you pipe it into standard views filter, and then you pipe it into standard views transform, and then you have this view object, and then you call an algorithm on this view object, right? So for those who don't know, although I was kind of bad-mouthing the iterator model, I actually think ranges are great. I was involved in the ranges standardization process. I've written an implementation of C++20 ranges. I particularly like this pipeline stuff. I think it's really nice. I think it's a really nice way to write code. So I wanted Flux to have this same capability as well. So like C++20 ranges, Flux provides a variety of sequence adapters that perform lazy evaluation. So what they do is, like views in C++20, they take your sequence and they give you a new sequence object, and when you iterate over that new sequence object, it calls back into the parent sequence, but modifies the way iteration is done in some way. Right? It's exactly as views work in C++20. And again, in the same way, we typically compose these into pipelines. So a pipeline begins with some sequence object, called the source, and then we pass it through 0 or more adapters, and then finally we call some algorithm on that adapted sequence. Right? Now this algorithm might be one of those algorithms we saw on the last slide, right? One of the named algorithms in Flux. It might be an algorithm that you yourself have written. It might be, as we'll see in a minute, an STL algorithm. We have a way you can call STL algorithms with Flux sequences. Or it might even just be a for loop, right? Because a for loop is just an algorithm you haven't given a name to yet. No raw loops, as a wise man once said. So I've done a lot of waffling about Flux so far. Let's actually look at some code. Let's actually look at an example of Flux in action. So starting off, we're getting a vector of integers, get vector. And then what we want to do is to calculate the maximum of the squares of the even numbers in this vector. Now, this is one of these kind of artificial problems that only ever comes up in slide code, right? But the purpose is not, I'm not saying this is a useful thing to do. It's a demonstration of the syntax, right? So the first thing you'll notice is this thing called flux ref. So unlike ranges, in Flux, we want to be really explicit about ownership and transfer of ownership and when that occurs. So if we want to iterate over a reference to the vector, that is, we don't want to copy or move the vector into the adapter object, we just want to operate on a reference, we use this explicit fluxref call. And actually, it doesn't say it here, but fluxref actually is a const reference. And if you want to be able to mutate the vector, you'd have to say flux muteref. Right, we've flipped the default for reasons that I might talk about tomorrow. So we're explicit about the fact we want to iterate over a reference to the vector. We want to adapt a reference to the vector. And then we build up our pipeline by first applying a filter transform. So right away, you'll notice quite a difference from C++20 views, because with views, you would say the pipe character, the bar character, pipe standard views filter, and then your predicate. In Flux, we build up our pipelines using the member function syntax. We say dot filter. And in this case here, Flux comes with a whole bunch of useful predicates as well. So we've got a ready-made predicate that says is something even. So we're taking our vector by reference, we're filtering it, retaining the even numbers. Then we're performing a map operation which squares each integer. So in C++20, this would be pipe standard views transform. But it turns out that pretty much every other language, every other library of this kind for every language, for you know, whatever it might be, they all use the term map. So from functional programming, the term for this is map. So Flux uses the term map as well for this operation, mostly because it's easier to spell and it's really common. Also because it's just the familiar term. C++ is really the outlier in calling this operation transform. So we have our pipeline, we start with our source, we pass through a couple of adapters, and then finally we have our algorithm call. In this case, the algorithm we're calling is a named algorithm, it's max, right, which returns you the maximum element in this adapted sequence. But actually, just if you imagine there's a little semicolon at the end there, then there is, as written, there is a bug in this code, right? And I wonder if anybody can spot what the bug might be. So, well, no, so we want the maximum of the squares of the even numbers. So, you know, we're happy to get whatever the square of the max is. That's okay. I mean, you're right, we'll get the squared value, not the original, but that's not the problem. No, you do get the value, so that's good. There is another algorithm called find max, which does return you a cursor. That's the equivalent of max element. No, the problem is, well, let me ask you, what would happen? Sorry. The vector is empty. Yes, okay. What happens, very good. What happens if the vector is empty? Or what happens if the vector only contains odd numbers? Because in that case, we're trying to find the maximum of some empty sequence. And what is that value? Now, okay, maybe for integers, you could say that's 0, but in general, we can't know what a reasonable value might be. So the max algorithm in Flux, it actually returns you an optional, right? It actually returns you an optional containing the maximum value. And so if you have an empty sequence and you request the maximum of an empty sequence, it's going to give you an empty optional. And otherwise, if the sequence is non-empty, it's going to give you the maximum, right? So as written, even if you put the semicolon, this actually wouldn't compile because you'd be trying to assign an optional into an int. So what you have to do is handle this in some way. In this particular example, I've chosen to say, okay, if I've got an empty sequence, then return 0. But you could just return .value, which would throw an exception, or a bit more complicated, but it would give you an error anyway. Or you could do an unsafe deref if you were absolutely sure that vector was not empty. So we kind of, as I say, as I've been trying to stress, Flux kind of focuses on safety, and we try and enforce this in lots of little ways. And one of those is things like returning optional here. So just as a counterpoint, there's an algorithm standard ranges max, which does the equivalent of operation, returns you the maximum value. Does anybody know what happens if you pass an empty range into standard ranges max? Can anybody guess what happens? UP, yeah, which is not great. So as with algorithms, Flux contains a really large number of sequence adapters. So this is the list as of about a year ago. We got a couple more since then as well. So these are, I think, it was at the time anyway, all of the equivalent of all of the adapters that were in C++20 and the ones that are in C++23, and I think all the ones that have been proposed for C++26, although that might have changed, so I can't promise that anymore. But anyway, there are loads because as I say, I really like this stuff. We're getting more all the time. There are a couple more actually that aren't on this list as well. So there we are. Yeah, got time. So, implementing the sequence protocol. We've just had a look at an example of how we use Flux sequences, how we build up these pipelines, how we call algorithms. What about the other end of the equation? What happens if we have some type and we want to turn it into a sequence that we can use with these Flux operations? How do we implement the sequence protocol? So who here has ever tried writing a range or an iterator? Yeah. Oh, most people actually. Was it a fun thing to do? Was it nice and easy? No, actually, I mean, I guess input iterators aren't too bad. There's quite a lot of boilerplate. But then when you start getting up to like random access in particular, like there's just an endless stream of operator overloads that you've got to implement. So one of the things I wanted to do with Flux was to make this side of the problem easier as well. So we've got this little type called myArray. It's pretty much the equivalent of standard array. The standard array already has an implementation in Flux. So we've got this type myArray. And what we want to do is we want to turn this into a sequence so that we can use it with our Flux algorithms. So how do we do that? Well, what we need to do is we need to provide a specialization of this class template, Flux sequence traits, specialized for, in this case, myArray. Okay, so this is a way in which we do customization in this library. There are other libraries that use this, like some Boost libraries use this form of doing customization. There are various ways of doing it. This is my preferred way. So we're going to have this alias self-t just for myArray. It just saves us some room on the slides. And then what do we do? Well, we have to provide implementations of our 4 fundamental operations. So we provide an implementation of the first function, which returns a cursor to the start of the sequence. So in this case, we've chosen to use size t as our cursor type. So first returns us a size t, and it just returns us a size t that's initialized to 0, the index of the start of the array. Next, we implement isLast that tells us whether we've finished. And in this case, we compare our cursor to the static size of the array. If it's greater than or equal to the size of the array, iteration is complete. And so we return true. We have our increment operation. And all this does is it takes the cursor type by reference, and it increments that cursor in place. And then finally, a tiny little bit more complicated is our read operation, read at. So in this case, we want to handle both const and non-const access to the sequence. So we can do that, combine that all into one read operation. So we take self as a auto ref, and we return decal type auto. And now we perform a bounds check. So we have this function in Flux called Flux bounds check. Actually, since I've written these slides, there's an even better function that's just called indexed bounds check for when you have an integer index, because that can actually do, in some circumstances, can do compile time index checking, compile time bounds checking, which is really cool. But I don't have any slides on that because it didn't exist a year ago. So we have this function Flux bounds check that does exactly what you think it does, right? So this is going to, depending on how you configure the library, either terminate your application, terminate the program, or it's going to throw an exception. There are configuration flags for Flux depending on which you prefer. And once the bounds check is out of the way, we're going to access the data array, and we're going to return the element of position cur. Okay, so we've got first, is last, inc, read at, and that's it. And having done this, my array is now a Flux sequence, and we can use it with all these sequence algorithms. And in fact, this is going to be a multi-pass sequence because size t is a regular type. So the Flux machinery is going to assume, we haven't opted out, so it's going to assume that, that my array is in fact a multi-pass sequence. And yes, we can static assert that in fact this is a multi-pass sequence. So this is, I think, sorry, yes, go ahead.
Would you use size t? Because people can clearly mess around with it themselves. Size t, they can assign 42 to it, things like that, or would you use a custom type to stop people messing around?
Yeah, so well, first of all, what happens if they mess about with it?
Well, it doesn't really, well, as long as they call one of these functions, the behavior is fine.
Yes, exactly. So there's an interesting question, and it's a kind of library design question of I could use like enum class cursor type, right? There are definite type safety advantages to doing that because, as you say, you prevent people. I mean, I guess they still could mess about with it, but it makes it much more difficult to mess about with. That is an absolutely valid implementation strategy. It would be a bit more code for the slide, but it would certainly work, and it's certainly a really good thing to do. There are downsides in that it's going to be a tiny bit more expensive in terms of like instantiations, I guess. That's a pretty weak argument. Actually, what it's going to prevent you from doing, at least by default, is from intentionally using the same, if you know that you've got an integer index, from using that same integer index to index into two different sequences, right? Which can actually be a pretty useful thing to do. You've probably done it with vectors yourselves, right? If you've got some index, you've found some position in this vector and you want to look at this thing in the same position in that vector. Now, if you use an enum class, you could probably cast from one, or you would be able to just do a static cast, I think. Maybe you'd have to go via an integer type in the middle, but you could certainly do that conversion. So that would be a perfectly valid thing to do. As it turns out, for Flux sequences, we just use an integer type. In fact, we use a signed integer type, and we use some checked integer operations because certain things optimize better if you do that. But also, I just like signed types better. But yeah, so that would be a perfectly valid thing to do. So this is one way in which you might implement the sequence protocol. In fact, there is a kind of a shortcut way that you can do this as well. So if you are the owner of myArray in this case, and if you don't mind modifying the myArray class, you can actually implement these sequence traits directly in the class. right? So you can do it like that, like this. You can have a public nested type called Flux sequence traits, and it's just exactly the same code, now written in the class instead. So this makes things a bit neater because you don't have to like escape from your namespace, and then do the Flux specialization in a separate namespace. You can just do this in class. So this is actually pretty neat. But if you're not the owner of my array, you can still do it the other way, the first way we saw as well. So I am of the opinion that this is considerably easier to implement than STL ranges. I might, you say, well, you wrote it. Of course you think that, but I think that this is easier, and I think it's very much easier when we go to higher sequence or range categories, right? So if we wanted to take my array and we wanted to make it a bidirectional range, we have one more function we have to write, which is dec. If we want to make it random access, there are two more functions. We add an overload of inc that takes an offset, and we add the distance function. Two more functions, or three more functions to get it all the way to random access. And you compare that to what you would have to do to implement a random access iterator, where you've got like 40, I think. Maybe it's not that, can't be that many. Anyway, 30-ish operator overloads, a crazy amount of work you have to do. The other thing you might have noticed is there's no iterator versus const iterator thing going on. So this is, particularly if you've implemented range adapters, this is a real headache. You have to implement your iterator, and then you have to have a const iterator as well. So what you do is you go back and template the iterator class on whether it's bool const or not, and then the standard requires that you can convert a non-const iterator into a const iterator. So you have to have a converting constructor, but only in the case where it's right. None of that. Handling const and non-const is in our read operation. If you pass a const sequence, then you get a const element, usually. That's why we had that thing with the decal type auto. So I think this is much nicer than implementing it than trying to implement the range interface. Okay, ranges compatibility. I said, well, it's one of the things I said at the start of this section was that I want to have good compatibility with STL ranges, because they've been around for a very, very long time. And even if I think Flux is the greatest thing in the world, I'm not going to convince many people to just stop using this thing they've been using for 30 years and use something new, right? That's probably not going to happen. So we need some sort of compatibility story. And so to that end, every C++ contiguous range, in fact, this is slightly out of date, it's now every random access range, is automatically a Flux random access range substitute. But let's say contiguous range is automatically a Flux contiguous sequence. Right? In fact, you probably didn't even notice, but we took advantage of this a few slides ago when we started iterating over an STL vector. Right? The reason for this is because if we have a contiguous range, then that's cheaply indexable, as in we can just get the data pointer and we can offset from that data pointer, and we can also do cheap bounds checking. So we contiguous size, this should say contiguous sized ranges, right? Because if we have the size, we can do a bounds check before we dereference any pointers. So this covers vectors, arrays, strings, string view span, raw C arrays, initializer lists, all sorts of things. You can just start using them with Flux sequences without having to do anything whatsoever. They just work. For other kinds of ranges, we can make them compatible with Flux by using a function called fromRange. Now, what fromRange does is it takes the iterator operation. In fact, it provides an implementation of that sequence traits class, and those functions are based on the iterator operations on the underlying range. Right? This is a way of bringing compatibility, right? But unfortunately, because those iterator functions are themselves unsafe, it means that we can't provide as many safety guarantees in the library if you're using this from range function. So it's no worse than using ranges directly. In fact, it's like the equivalent because we're just calling the underlying iterator operations. But it's just something to be aware of. If you know, it's a compatibility measure. It's pragmatic. It's because I want people to have an easy way of moving to Flux. So it's a compatibility thing. Going in the other direction, the news is even better, because every Flux sequence is an STL range, right? Every Flux sequence is an STL range. We provide STL-compatible begin and end functions that return iterator and sentinel, meaning that if you have a Flux sequence, particularly if you have some like adapted sequence that you've built up, you can call C++20 algorithms. You can even use C++20 range adapters if you really want to. In particular, it means you can use Flux sequences with range for loops in the language, which is really nice, right? So I've done everything I can to try and make Flux work well with the existing infrastructure we have. The way we do this is we have this type Flux called sequence iterator. This holds a pointer to the sequence and the current cursor position, right? So this is holding a pointer. This can potentially dangle if the sequence goes out of bounds, but you know, this is iterators. We know that they're unsafe, right? So we're not losing anything by doing this. And yeah, you can see we implement all of the iterator operations in terms of the equivalent Flux functions. And this goes all the way up to like randomax or contiguous even. So yeah, I laboriously implemented all of these things, so you don't have to. Right. We're nearly there. There is one more thing I've got to talk about. There's one last thing I have to address, and that's this fella. I said the elephant in the room that you've all very politely been ignoring and not raising your hands to ask about, and that's performance. Because in particular, the read operation is bounds checked, and this gives this makes people nervous, right? Because they're thinking, well, you know, can I afford these bounds checks? And it turns out compilers are incredibly good at eliding, that is, removing bounds checks when they can see that they're unnecessary, right? And this is, I think, because pretty much every language I can think of from like the last 30 years or something, they use bounds checking on whatever their native array type is. It's probably going to be bounds checked. Maybe there are new languages that don't do this, but they're pretty rare. And so optimizers are very good at kind of recognizing these patterns. The other thing is, if you actually think about how we would iterate over something, you do your end check, right? And this says, well, is my cursor past the end? And then the very next thing you do is a read operation, which says, is my cursor past the end? And the compiler's going to go, well, I've literally just checked that, so I'm not going to bother checking it again, right? There's also, I briefly mentioned it, I've got a blog post about it on my website if you're interested, but we do, with Clang and GCC, sometimes we can do compile time bounds checking as well, which is really cool. So then it's completely removed from the runtime code. So I've got a little example that it turns out that people couldn't read when I put this on the thing last year. But I'll very quickly go through it. So we've got this function count evens. It just uses the traditional range for loop to go through and count how many things in this vector, or how many integers in this vector are even. And then I've got the equivalent Flux version. So this uses this macro flux for. Does a for loop, but it uses the Flux primitives to do it. It uses fluxing, flux read at, etc. To do the iteration. Mostly I use it for testing. Because you want to use a range for loop normally. The reason I don't is because Flux is, if we try to use a range for loop over the vector, it's just going to use the vector interface, right? So this is forcing it to use the Flux interface as well. And again, I don't expect you to see this because I was a bit optimistic about how big the screens were going to be when I put these slides together last year. But basically, there's a diff between them, but fundamentally the inner loop kind of has the same shape, and the bounds checking has all kind of disappeared. And as I say, this implementation is using this Flux 4 macro. It's kind of, I use it for testing. It's available for public use, I suppose, but it's not intended. The intended way to use Flux is to use a named algorithm where one exists. And in this case, there's a named algorithm for counting things, and that's count if. So we want to count if things are even. So here we are in this case, and have I got it? No. So if you look at the bottom, you might just be able to see it. The bit that's highlighted in red on the left is Flux count if, and we've passed it a predicate. So it's a nice one-liner. And now this is the diff between the two functions, and you can see that other than the function name, the entire generated code is identical, right? Bit for bit, identical to the imperative version using the for loop. So how does this work? Well, Flux has this neat optimization trick which is based on internal iteration. So there's an extra customization point, one I haven't talked about so far. It's an optional customization point. It's for each, called for each while. And what this does is it says to the sequence, here's some predicates. Just iterate over all of your elements, calling the predicate for each element in turn until such time as the predicate returns false. And at that point, iteration is going to stop. Right? So this kind of, it's like abstracting a for loop in that it says to the sequence, whatever way is fastest for you to iterate over your elements, just do that. And if the predicate returns false, that's like a break in a for loop. Tells us to exit. Otherwise, we're going to continue until we reach the end of the sequence. So it turns out that many sequence implementations can do this quite efficiently, but in particular, many sequence adapters can be really efficiently written they provide a specialization of for each while, which calls a specialization of for each while on their parent in the adapter chain, which calls a specialization of for each while on the parent, etc., until we get to the top level. And I wish I had more time to go into it, but this is really, really, really well optimizable, if that's a sentence. The compiler can optimize this really, really well, right? Because you end up just passing a lambda into a lambda, and the compiler's generated all this code, and it can see straight through it, and it can inline everything, and this just optimizes wonderfully. And many algorithms can be written in terms of a call to for each while. So any sort of fold, reduction, find if, min, max, all of those sorts of things. Pretty much anything where you take a single sequence and you iterate it from the beginning until some point, you can do this internal iteration. And what this means is that Flux pipelines, in many cases, can generate more efficient code than the equivalent C++20 ranges pipelines, in some cases really dramatically. So one little example of that here. So here I've got again, we're going back to summing the squares of some even numbers. So this is a pipeline that's using C++20 ranges. So we're taking our vector, we're piping it through standard views filter, we're piping that through standard views transform, and then we're calling standard accumulate to calculate the sum of these transformed filtered elements. So this is how you do it in C++20. C++23, you'd actually you have a fold left operation, so you wouldn't have to use accumulate. But that's how you do it in C++20. And here's the Flux version. So we're taking our vector by reference, we're calling filter, retaining the even elements, we're squaring every element, and then we've just got this nice algorithm called sum, because that's easier to spell than accumulate. Right. So this is the generated code. The Flux is on the left, ranges is on the right, and the thing you'll notice is that Flux is generating a heck of a lot more assembly. And you're thinking, well, this is what's going on? I thought you said this was better. You may not be able to see it because this is all very small, but actually, if you look on the left, the Flux code, we've got all these lovely AVX instructions in our code, because with the Flux simplified internal iteration model, the compiler's been able to see through all of our inline functions, and it's been able to go, hey, this is a nice simple loop that I can auto-vectorize, right? So we're getting auto-vectorization with the Flux code, whereas in the ranges case, the optimizer can't see through it quite as well, so it hasn't been able to vectorize. So typically, implementations of for each while don't need to do any internal bounds checking. That's another advantage, because we're not exposing any cursors to the user. That's the internal part. It means that the user can't mess about with our cursor position, so we don't have to worry about it being invalidated. We can trust that our implementation gets things right. And as I say, in many other cases, compilers can optimize away bounds checks. What, though, about corner cases? What about, I've looked at this, I've profiled this, I'm seeing that there's a bounds check still in my code. It's costing me 1% performance, and I can't afford that. What can we do about it? Flux provides another optional customization point that's called read at unchecked. And this does exactly what you think it does. It does a read operation without any bounds checking, right? So this is an unsafe operation. It's the equivalent of just the square brackets operator on an array. So it's unchecked, but it has no bounds checking overhead. You can use this selectively where you've measured, where you absolutely need it. And you can kind of think of this as the equivalent of unsafe blocks in languages like Rust or C#. When you need the absolute best code that can possibly be generated, and you can't use internal iteration for some reason. All right, that is it. So thank you for bearing with me. I think that actually went all right, didn't it? That was, for a talk I haven't given for like a long time, I managed to drag it out of my memory. So Flux is a modern C++ library for what people call sequence-oriented programming, collection-oriented programming. It can be used anywhere that C++20 ranges can be used. It's safer, it's, I hope I've convinced you, easier to use. It offers compatibility with existing STL code, and in many cases, better performance, that is, nicer generated code. So that is my advertising pitch. That's where you can find Flux. I've got some documentation there as well. That's my, it should say X now, I guess, but that's it. So thank you very much, everybody.